Hello, my name is Denys Chernyshov, and this is Eternity Live Forum's interview with the speakers who will perform at the forum at 11th of November 2022. Eternity Live Forum is a major event, a concentration of experience, knowledge and research from a number of scientists who will present the latest developments and ways to increase life expectancy and perhaps achieve immortality. So we are glad to welcome our viewers to an interview with an interesting person, great professional, PhD, Master of Medicine and Neurobiology, Michael Fossel. Hello, Michael.
For having me. I appreciate the opportunity.
Thanks. Michael, our forum is dedicated to research and new discoveries in life extension and immortality. What research are you currently undertaking in life extension?
We actually believe that we can actually reverse aging. That is, not just ameliorate it or slow it, or stop it, but actually reverse aging process. And I base that on a lot of data over the past two and a half decades. So our initial target is going to be age-related diseases, and specifically we're going to start with age-related neurodegenerative diseases, Alzheimer's, move on from there to age-related cardiovascular disease, and show that we can actually reset the aging process at the most fundamental cellular, genetic, and epigenetic levels, and thereby cure and prevent age-related diseases.
Right. Great news. So how do you think, is there any tangible progress in life extension research already?
It's funny you should ask that, because if we went forward 50 years and we said, when was the first time we ever actually showed we could reverse aging? The technical answer is 1998. And when we first showed that we could reverse aging in human cells in the laboratory, in an article published in Science magazine by the Geriatrics group in California. And what they showed is they could take human fibroblasts and reset the aging process entirely. And the first time we ever did that in human tissues was in the year 2000. And that was a paper also by the Geriatrics group showing we could do that with human skin. It is, you could take old human skin and regrow young human skin in the laboratory, actually on mice. And that was followed by an article showing you could do this in bone tissue and in advanced cardiac disease. That is, you could take coronary artery tissue from older people and grow young coronary artery tissue. So we've known we can do it in human cells. We know we can do it in human tissues. The question is, can we do it in an organism? And the first paper that ever showed that in a useful way was 10 years ago. It was Maria Blasco's work out of Madrid, from CNIO, showing she could do this with an AAV vector and deliver mouse telomerase gene and reset the aging process within the technical limits of our ability to do this. So that's the sort of progress that we've made. So if anyone, I think most people in this field think you can sort of slow the aging process, or as I say, treat the symptoms, without realizing you can do a great deal more than that.
It is a very exciting news. And which technologies do you consider are the most significant for life extension?
There are two sorts of questions. One is, what is your target? And the other is, what's your technology? Most people are targeting downstream biomarkers. They regard biomarkers as the thing to go after. And that would be like trying to treat COVID by treating cough. You're targeting the wrong thing. What you really need to do is target not the downstream biomarkers or the upstream risk factors, but the central process of cellular aging. So that's the target we should be using, and most people aren't. They're still going after mitochondrial dysfunction, or they're going after a number of senescence-associated markers, but they're not targeting the actual process. They look at it as individual pieces rather than understanding the entire system. The other, though, is a question you've asked, which is the technical approach, and that's still in many ways up in the air. I think that in regard to our technical approaches, it's much like the Wright brothers in 1903. They have demonstrated powered flight for 12 seconds, but they have not got an Airbus 380 going over an ocean with carrying hundreds of people safely. That's sort of where we are with gene therapy and with some of the technology we're using. We have proven it works, but it's not as good as we'd like it to be. The most promising technologies from my standpoint are either to use a delivery of a telomerase gene or delivery of the mRNA for telomerase, and both of those are exciting possibilities.
Thank you very much for such an interesting answer. Do you believe that science and medicine are capable of achieving immortality for humans in the future?
Not in the absolute sense. That is, you can always get hit by a meteor, or you can always have problems in Kiev. There are always things that will happen. But in terms of aging, yes, I think we can show that we can effectively reverse and prevent aging. Now, let me give another exception to that. there are things that happen to us that are accumulations of damage independent of aging. So, for example, if I'm a tool and die maker, I may lose a finger. And if I live 1,000 years, I may lose all my fingers. That's not aging, that's simply accumulation of damage. Or a more realistic example, if I'm a miner, I may get exposed to silicon dust. And the silicon dust exposure and what it does to my lungs is not per se an aging process, it's an accumulation of damage. So when you're looking at that sort of thing, that we would have to deal with independently. But as far as the aging process, yes, I think we can stop and reverse the aging process and use that to cure and prevent age-related diseases.
These are really great. And which technologies do you think will support immortality most of all?
Again, the question from our standpoint is, what's the optimal point of intervention clinically and financially? So I'll give you another sort of extreme example. I can treat heart disease by doing a heart transplant. It is expensive, it is dangerous in many ways, it has a lot of side effects, it doesn't have a long life profile. It can be done, and you could use that to treat heart disease. It's not an optimal approach. The same thing I could do with, I can use stents, I can use coronary bypass grafts, I can put you on statin drugs, I can control your blood pressure. All of those have a degree of efficacy and certain costs and risks. The question is, where's the optimal approach, for example, to cardiovascular disease? And the same thing is true with regard to treating aging. You know, we can treat all of the downstream biomarkers, we can try to treat all of the upstream risk factors, but when we look at the central process of cell aging, the same question pertains, which is, where's the optimal point of intervention? For example, we know that as the telomere shortens, it changes the epigenetic pattern, the pattern of gene expression downstream, and that changes things, for example, the turnover rate of molecular pools. So I could treat the molecular pools, I could treat the particular gene involved, for example, for cytochrome C oxidase, where it turns down the rate of turnover for mitochondrial function. I could treat all those little things, or I could go upstream and try to prevent cells from dividing, or I could try to prevent telomeres from shortening, or I could re-lengthen telomeres. I could use telomerase, I could use mRNA, I could use the gene, I could use the protein. There are all these questions. And so the question from our standpoint, again, is where's the optimal point of intervention? And it looks like the optimal point of intervention is to have telomerase function well enough to re-lengthen telomeres when we lose telomere lengths. That's yet to be shown in clinical trials with human beings in, for example, phase 1 human trials. But from our perspective, that's the optimal target right in that area, that sweet spot. And then the question again is, what's the best technical approach to use for this? And that's still something that we're trying to determine by running some dual trials in the next few years.
Thank you very much. And the last question. In your opinion, what do we need to investigate more at this stage in the study of immortality?
I think what we need to do is take what we know and go to human trials. The biggest problem I see is that people have a great deal of knowledge but little understanding. I remember when back in the 60s actually, when I was taking calculus, people would memorize the formulas, for example, for the area of the surface of a sphere. I didn't memorize formulas, but I knew how to derive them using calculus, and I could integrate and get the answers again. So I understood where they came from, but it wasn't that I knew the data, the formula, I understood it. And we do that with aging. We know a great deal, enormous amount, about age-related changes in cells and tissues. But what we lack is an understanding that it's a unified systems approach to how the entire process works. And that's our biggest obstacle.
Okay, that's great. Thank you very much for such an interesting opportunity. It was really, really great conversation. And thank you very much. And I see you at the Eternity Life Forum.
Forward to it. Thank you, Denys.